I need a thumbnail. I hate thumbnails. How do I do thumbnails? How do I get a thumbnail? I don't want gaming either. Edit. Category.
Math.
Education. Thumbnail. I'll just put
EGMO.
download. HB. What the? Download. What was download?
It's a JPEG, so.
Is there like a picture of myself somewhere?
This generic image. Oh my god.
A backup photo, that's it.
So this is like the one photo of you everyone in the world has seen. It's just this one. Michael before Wade.
Another good thing is you don't need storage to live stream and record.
Oh, someone said something to on Discord.
A bit late, maybe 3.
Oh, more speed running.
Alright, 17 minutes. Well, I got 17 minutes of stuff that he probably already knows from last time.
Okay, Dan, I wasn't.
Yeah.
Recording in progress.
Okay, so if you recall from last time, like, me and Liam actually looked on this problem, okay? And Liam basically did almost what you did, but then for some reason got stuck. And then I came up with this funny example, so we ended up solving part B before part A. So the example for part B was, okay, so the question was, like, a divisor, and so n such that, it's here somewhere, yeah. Show there are infinitely many n, which are 0, 1, 2, 6, 5 mod 7, that has a divisor of n to the 4 between n squared and n squared plus 2n, yeah? And there's none that are 3 or 4 mod 0. There are none that are 3 or 4 mod 7. Yeah. Okay. So you came up with this example like this: n equals 2 times AB, right? And because it has to be a composite number, yeah. And so we essentially come up with like AB, and then the 2 kind of makes it work, yeah. So n equals 2 times AB. And the divisor is equal to n squared, so like 4a squared b squared plus 2b squared. Okay, so essentially you're like killing a factor and you're adding another factor, yeah? So the motivation is like, imagine if they were primes, yeah? And then a lot of what happens is forced. Okay. So then you want to say this divides n to the 4, right? Yeah. But the point is, like, this is equal to 2b squared 2a squared plus 1, right? Which is co-prime to a, right? This part. So that means the a squared plus 1 has to divide the b squared, right? So 2a squared plus 1 has to actually divide b squared. Yeah.
So B2.
Yeah, maybe Liam can join to monitor the chat.
Alright.
Just in case anyone joins the chat.
So, am I the chat monitor? I'll
Keep
take
you more
my
engaged.
steamed position.
The choice squared plus 1 is profound.
Maybe Alex, you can join anyway. Just join to see if it works.
No one has said anything in the chat.
That was it.
I said something in the chat.
I can't see anything.
Michael,
No.
your video's all black.
Is it?
Yes.
You forgot to.
It's not working.
Mhm.
Why is it not
Go
working?
to OBS. Is OBS streaming anything?
Stream set.
Wait, is it not live?
Like, no, OBS display caption does not work.
Kind of technical difficulty.
Well,
This is working now, right?
Yes, sir.
Yes, it's working. Okay, good. Yeah, so the problem is to find n such that there's a divisor of n to the 4 between n squared and n plus squared plus 2n, yeah? Alright, so yeah, so you have 2a squared plus 1 divides b squared, yeah? Yeah. And we know that, because we just switched out a for b, we know that b on a has to be less than 2 for this to work, right?
be on A.
That makes sense? Because this part has to be less than 2n, right? Because this is n squared. And this has to be less than 2n, right? And the only difference between this and n is you swapped out the a for the b. So it's b on a. So times it by b on a. Yeah?
So this has to be 2b is the square less than 2.
Yeah.
Okay, you divide those.
So then b squared has to also be less than 4a squared, right?
Oh.
Or less than or equal to, whatever. Okay. So for that to work, like b squared actually has to just equal 2a squared plus 1, yeah? Does that make sense? Yeah. Okay, so actually, you know, I mean, I realized, like, I should have realized it more instantly, but I kind of did immediately realize this was a Pell's equation, right? And it's much easier to see that's a Pell equation than the one that you had, because you had to complete a square. Okay. So basically, this example works if you can solve this Pell's equation, right? Okay, and we actually solved the Pell's equation with continued fractions last time.
Whoa.
Yeah. Do you remember we were ever doing that?
Yeah, I guess like.
Okay. But anyway, Alex came up with a pretty good way to solve this without continued fractions. I don't know if you were paying attention, Liam.
Yeah, you could solve Pell's equation.
I said without.
Without?
Yeah.
Oh.
So actually, all you need to know is that there's infinitely many solutions. And then you can solve this. Because I think what Alex did is, okay, so what we got out of this was 0, 2, and minus 2 mod 7, right? Or 0, 2, 5.
Yeah.
I think Alex can get 2 and 5 out of this without actually knowing what the solutions are.
I think I can get 0 as well, as long as I get one solution.
Oh.
If I continue.
Yeah, like if you get 1 for 0, because what? Oh wait, actually, this is how I think this is what I heard of the argument. Yeah. So you can either get 0 or plus or minus 2. That's what I've memorized it as. So if you know there's infinitely many solutions to Pell's equation, right?
Yeah.
Okay. Okay, first of all, it should be clear, like if you do some mod arguments that like a times b can only be like 2 or 5. Oh wait, can only be, let's see. Like what can a and b be mod 7? Like squares mod 7, right? Can be 0, 1, 2, and 4, yeah? So those are the only squares mod 7. So, and how many of them have like difference equal to 1 times 2, yeah? So 0, so 1 minus 0, yeah, equals 1. 2 minus 1 equals 1, yeah?
Wait, 2. Oh, yeah.
What else is there? 1 minus 0, 2 minus 1. Like you can't really get, like 4 minus anything doesn't work, right? Like these are the only possibilities, would you say? Yeah? So B and A, it's like 0 and plus or minus 1. Or it's like plus or minus 4 and plus or minus 2, right? And so N is either going to be 0 or it's going to be plus or minus 2, right? When you times it by 2, yeah? So N equals 2AB, yeah? That makes sense?
Yeah.
Yeah. So as long as you know there's infinitely many solutions, right?
Yeah.
You can use the pigeonhole principle to say that infinitely many have to sit in one of those mods, right?
Yeah.
So, so that's what I was saying, like, because he had this idea with homogeneous as well. See, like, it's not it's like kind of homogeneous, but basically, like, if it's homogeneous, you can scale B and A by minus 1, right?
Yeah.
So if you can show there's infinitely many solutions which have 2, right?
You can show this information. You made the 5.
Actually, is that true? Can you just make it negative? Yeah, you can just make it negative, right? But the problem is,
Wait, what is. Divisor?
the problem is, I think n is cancels the sign. So n.
I have this dumb idea.
Hmm. Yeah, I guess the problem is you're changing 2 signs at a time. But what if you just change 1 sign? But then n will be negative now, yeah?
Hmm.
Okay, well at least you get one of the 3. How would you finish it from there then?
My idea was with the square
Oh,
of an exponent.
squaring, huh?
Not sure if it works though. Works for it worked for one case on mine.
Yeah.
But like no.
Yeah, like I guess like in the exam, it's good to come up with some kind of like life-saving device. But outside, it's probably best just to learn how to solve Pell's equation. Um, yeah. So last time, I don't know if you remember, we showed that the continued fractions. You remember we have like root. So this is a continued fraction for root 2, right? And we showed that it's equal to 1, comma 2 repeater. Yeah. And then
It gives you like
every second one is a solution to Pell's equation. So like 1, 1, 2, 1, 2, 2, 2, 1, 2, 2, 2, 2, 2. These are all solutions to Pell's equation. Yeah. Yeah. But yeah, I guess the thing Liam never pointed out was, like, are these all the solutions to Pell's equation? Okay.
Sus. Also, do they get the correct mod time?
Yeah. Yeah, so with Pell's equation, it's easy to get the mods. Should we show Alex?
How does this work?
So do you know how to? So you know how to get continued fractions? It's like
There's like,
one
yeah, there's
plus
like a
one on two plus one on two plus one on two, right? But it's like, but it's also equal to like Pn on Qn, and there's a recurrence for the Pn's. So once you know like a bunch of them, so like for example the first one, like P1 on Q1 is just 1 on 1, you know? P2 on Q2 is just 3 on 2. And then once you know that, then like you can get the next ones. It's just 2 times the previous ones plus the previous one. So this is just 7 on 5.
7 on 5.
And P4 on Q4.
This is recurrence.
And you just times it by 2, so 14, 17 on
Eventually
12.
it should like.
Yeah, like if you do it mod 7, it's just gonna cycle, you know?
Oh yeah, and then eventually you just get infinite.
Yeah. But then the thing you got to remember is like this is not a solution to Pell's equation. Only this one is.
Have to skip
this. Yeah, these ones give you -1. So there's a thing about continued fractions, like the odd ones, like are above, and the even ones are below, or whatever one. Like the even ones are below the approximation. Like one of them is the one side of the approximation, the other one's the other side. You know what I mean? So like the odd ones will all get you negative. And the even ones will all get you positive.
What is happening?
Okay.
I see, so it just solves using this.
Yeah, like this tells you like all the solutions, yeah. But the thing is, Liam,
Yeah.
we never proved that. We actually proved that. So when you have a square root of a square root, right? The continued fraction is always like it's kind of like this. It becomes periodic in this part, all the way up to 2a1, and it kind of goes up onto the middle, and it comes back down to back down. Like it's like a palindrome, and then this whole thing repeats, yeah. And it's basically saying that whatever this number here is, so how many times it gets to there, like that that Pn and Qn, yeah. Does that make sense? Like if we call this position L, yeah, then PLQL is a solution to the Pell's equation with -1 to the L. Does that make sense?
So it gives you -1 10.
Yeah. I don't know. Do you want me to send you the recording for that? That was the one that had the 1K live subscriber live.
Oh.
If you want to see it, yeah. But anyway. Yeah, but so the problem is obviously like if L is odd, that it's not like a solution because it's -1. But if you just do it twice, it'll be even. You know what I mean? Yeah. So I guess what I want to work on right now is the converse. So the whole idea is Pell's equations, they're meant to give you approximations to root, like if it's Pell's equation for 2, it's meant to give you approximations to root 2, okay?
Yeah.
And continued fractions are somehow meant to be universal with respect to approximations. Rational approximations.
It gives you more.
Yeah, so the thing I want to prove is that like if something is if a rational is a good approximation for root 2, then it has to be one of the things in the continued fraction for root 2. That makes sense?
Why would that ever be?
Yeah, so I got an article we can follow, but I kind of want to see if this premise makes sense. So you have so this is like your root 2, right? And you have a fraction r over s. Remember what's the condition for the approximation being good? You remember?
It's like 1s.
Yeah, like it's like yeah. Yeah, 1 on s squared. Okay. In this case, we can even get it even smaller, 2s squared.
2s. Well,
Yeah. You might want to note that. See, because if you have x squared minus 2y squared equals 1, right? Yeah. Then you get x minus 2. Obviously, x is bigger than root 2y, right? It's going to equal to 1. So this is positive, yeah? And it's equal to 1. It's equal to x plus root 2y.
whoa.
Yeah.
Plus root 2.
So if you divide both sides by y,
Oh, then you get x over y. And that becomes y times x plus root 2y, but then.
yeah. But the point is x is bigger than y, right?
X is big. Therefore, this
So it satisfies that property,
is
yeah?
less. Yeah.
Okay. And so then what we want to prove is anything that satisfies this property,
So if it is good approximation, it is continued.
then it's part of a continued fraction, yeah?
What? That's crazy.
Yeah. So the start of the proof looks like this, and I want to take a moment because I want to know if this makes sense, okay? Because it probably does make sense, but it just kind of it's a lot to take in one go, yeah? So it's like it's actually it doesn't have to be root 2, just any x, you know? But alpha maybe, but let's just take root 2 for now.
Is this any number?
Yeah. So if you do like so if you take like r over s, yeah, and you write out the continued fraction, a1, a2,
Ooh.
and make this a k.
Wait, so if it deviates from the original one, you prove, oh shit, it's off. It's off.
And then root 2. So maybe let's call this alpha now. I'm kind of sick of this. Root 2. So alpha is actually easier to write than. But this is the funny thing. So is it true that you can always write alpha like this? So this is a mega sus abusive notation, okay? So
This is like this is some random alpha.
yeah, so this alpha k plus 1, okay? Literally is like it could be negative and stuff. Okay?
What the?
That makes sense. Because like you can't assume that this is true. Like if you assume it's true for like a legit alpha k plus 1, then you're just assuming the conclusion, right?
Alpha. Yeah.
Like we're supposing that alpha is approximated by R of S, yeah?
Yeah.
Bruh.
And then we're supposing that R of S has this legit continued fraction, yeah?
Mm.
But now we're supposing alpha has that legit continued fraction continued to one more term, yeah? Yeah. But this is not a legit continued fraction.
Mm.
So here we just have alpha k plus 1. Like it's a real number.
Yeah.
Does that make sense?
Yeah.
Mm.
I think you're not really understanding
Like,
what's
can't
going
be
on.
zero, because otherwise you have to
Some
divide
things
by-
can't make sense too fast, okay?
True.
Alpha can't be. Hmm.
So basically what you're saying is
If it's negative, it's illegal. So we have to prove it's positive. So it's legal. I see.
but you're basically saying that like there always exists something you can write like this, yeah? So you kind of like you can solve this for alpha k plus 1.
It has to be positive.
Yeah, I mean it's kind of believable, right?
Hmm.
Because you just do like alpha minus a1
Is it true? Huh?
and 1 over that equals a2. I
Is
mean,
that really true? What's
yeah, so as long as alpha is not equal to a1, which it's not, and then this is not equal to a2.
hmm.
Yeah, so as long as alpha is not equal to R on S, then this thing probably works, yeah?
Probably.
How do we prove it works then?
I don't know, bro. Let's see. I guess the sign depends on if it's like greater than or less than. RNS is greater than or less than the thing.
Yeah.
How do we know that? RNS. RNS equals this big. That's the problem, like, because if it's on the wrong side, it's negative. Though.
Oh, Justin's yeah.
How is this possible?
Alright, Justin, can you hear me? Justin? I might have to turn my volume up.
Damn. A3.
Justin, can you hear me?
AK plus 1.
Justin, can you hear me?
Check OBS.
Wait, do I just have no sound or is... Oh wait, is he not joined? Wait, do I have no sound?
Seems like you have some.
You have an issue with not having sound.
Wait, Justin, can you type if you can hear me?
Oh wait, no.
Are you also talking?
Alright.
Are you trying to make sound? Because I can't hear anything. Oh, on a different device. Okay, as long as you're not talking. Okay, his mic's broken. Okay, that's fine. Alright, so what we're doing now is we're proving some sort of converse to what we proved last time. So last time we proved that if you take the sort of what's called the partial quotient of the continued fraction for like root 2 or something at sort of the part where it starts to repeat, then the numerator and denominator satisfies the Pell's equation. Yeah. Now we're trying to show that anything which satisfies this kind of approximation property. So any fraction r over s which is within 1 on 2s squared of alpha has to be part of the continued fraction of alpha. Has to come from the continued fraction of alpha. Okay? And so we're trying to start the proof like this, but I'm trying to convince you that this actually makes sense. So you assume that alpha has a rational r over s. So r and s are integers such that it's within 1 on 2s squared. Then we write the continued fraction for r over s up. And then we write something that kind of tries to be like the continued fraction for alpha, with the exception that this number could maybe even be negative. So we're basically writing it like this. For some alpha k plus 1, it doesn't have to, like, if it's positive, I think if it's positive, well, at least if it's not negative, it has a chance to be a continued fraction. But at the moment, we're just trying to be like a continued fraction. We haven't actually shown that this is a continued fraction, okay? Okay, so the question is, do you believe that there's always an alpha k plus 1 such that this is true no matter what alpha and a are? Yeah. So you're kind of just like maybe trying to solving for alpha k plus 1. Yeah. That equals alpha k plus 1, yeah. Yeah. And also, I think, do you guys remember about finite continued fractions? You remember finite continued fractions? So, like, key theorem was like, a continued fraction is finite if and only if the number is rational. Remember this?
Yeah.
And then there was one little thing was that, like, a finite continued fraction, the length could be extended, like, it could be even or odd length.
Oh, yeah,
Because you can always do the plus 1, yeah.
Wait, that's smart.
You can always do some kind of trick with the length.
Oh yeah, you can like put 1 at the end.
Yeah, so it's not completely unique. It's like, it's almost unique.
Oh, so then you could like add a 1 at the end. And then you can like force it to be the right sign. Wait a minute.
Wait, okay, so what do we actually need to show that this is a continued fraction, yeah? So we need to show that alpha k plus 1... Do we show that alpha k plus 1 is greater than or equal to 1? Is that what we need to show?
Probably.
So I just want to get this straight, because if we can focus on this, like at worst we're just reading an article. Okay, so
What happens if it's not greater than?
if we can show alpha k to k plus 1 is greater than or equal to 1, okay, then essentially the fraction continues, right? You can keep continuing.
If it's less than 1, then the continued fraction is wrong.
If it's negative, it's just illegal, right?
There's no way.
But if it's like, what if it's like less than 1? Then it becomes like 0 plus something,
It's
right?
less than 1.
We can't have 0 in our continued fractions, can we?
If it's less than 1,
It's 0, then it's rational.
Yeah, we can't have
I
0.
want-
If it's 0, you divide by 0. That's
can't be 0.
No, like it can't be like 0.3 even, like.
But
yeah.
I was.
Yeah, because the way continued fractions work is like the fraction part is always going to be greater than equal to 1, right? Yeah, because you're flipping it.
Yeah, exactly.
It's like less than 1, then you flip it, right?
So, like, therefore, this is unique.
Yeah, so if we can show alpha k plus 1 is greater than equal to 1, then we're done, right? Okay. This is, I found this website, which is supposedly having this proof here.
Crypto. This is such a.
Oh damn, crypto stands for what? They're doing like cryptography and they're like, oh shit, we need
The thing is, we probably should be able to do this without looking at this. And there's only so many ways you can proceed, right?
Oh yeah, they are showing it's greater than equal to 1.
So it's pretty much the same thing up to here, right?
Yeah, okay, now what do we do? Improve.
So in our case,
We need to do some mess.
we have alpha equals pk alpha k plus 1 plus pk minus 1. We're all familiar with this thing, right? Yeah?
Probably.
So basically, it's the same as the recurrence. Remember the recurrence for the p's and q's? Except it's like an abusive notation.
You need to like put the alpha instead of the.
Yeah. So like you're thinking of it as a finite thing, but then your thing's not an integer anymore.
But it still works.
Okay. Okay, so then I think they solve for alpha k plus 1, yeah? And solve for alpha k plus 1. So alpha k plus 1, alpha qk minus pk
Oh yeah, it's literally the
equals pk minus 1 minus alpha qk minus 1, yeah?
alpha by itself. Oh, and it's not that six. So a little bit multiplied.
Okay. So then this is right, yeah? So we're trying to show this is greater than or equal to 1, yeah? Okay, as k is odd, we have that so x minus pk on qk is between 1 on 2 qk squared and 0. Okay, so they're assuming that they know the fact that like the odd parts are all like below the x and the even parts are all above the x. Okay?
Whoa.
That's kind of like how for root 2 it's always plus or minus 1.
What's the x? Wait.
the alpha. It's alpha.
The alpha. Okay, so alpha's the target, and then we have this sus thing that's like if it's odd. Do we have that? What's hold up a minute?
Oh, okay. So this thing here, alpha k plus 1,
How does this work? So it's like alpha
k plus 1
so you have this
equals,
rational.
so you have alpha
Are they just
outside of
assuming that? What
over
the x minus q?
so it should look like that, yeah.
I'm so confused.
What about which?
So we got x k. Wait, we got alpha k plus 1. How do we know it's positive? How do we know it's greater than 1?
Oh, we don't yet, do we?
Don't.
That's the conclusion.
Oh, a pk.
Like if we can prove it's greater than 1, then we're done.
Uh, how do we know x is x minus pkqk? Like that, because like that's the approximation that we have. It's not the. We don't know if this continued fraction is the one we want.
Hmm. Hmm. I feel like the thing's upside down to what we have.
What's going on?
Oh, oops, I did it upside down. This equation should be... Okay, let me just rewrite this again. So this thing here is equal to... It's this over that, yeah? And then you get out the QKs and the PKs. And you get alpha k plus 1 is equal to it's equal to pk minus 1 on qk minus 1 minus alpha instead of qk minus 1. And then the bottom becomes alpha minus pk on qk. Yeah. So the bottom is actually just epsilon qk. Huh. So this thing should just be like alpha minus that is the epsilon. So it's epsilon qk down the bottom, yeah? And then there's some kind of 1 minus thing at the top. How do they get that at the top? It kind of feels like they just kind of artificially inserted. So like if you just have just replace alpha by epsilon plus pk on qk, you know? So pk minus 1 minus epsilon plus pk on qk times qk minus 1. Oh, okay, I kind of see what's happening here. Do you guys see what's happening? We'll have to examine this after I do this. So we're at this step here. Here is this. Okay, so you remember this identity where it's like Pn Qn minus 1 minus Qn Pn minus 1 equals minus 1 to the n? If you don't remember that, assume that, because that's going to come up. So you times top and bottom by Qk, and you get Qk Pk minus 1 minus epsilon Qk minus 1 Qk minus Pk Qk minus 1 all over epsilon Qk squared, right?
So
Does that make sense?
I just don't get like the x minus p k over qk.
Equals epsilon. Which part? So that, I guess that's the assumption, yeah. Like the assumption is that
Alright.
yeah. So
Well,
pk
assumption?
so pk over qk is r over pk equals r and qk equals s.
No, like I don't understand like because how do they know that?
It's positive.
Yeah.
Oh, so basically we could probably verify it directly at some point, but
Because like they're just assuming the absolute value.
yeah, so there is a theorem that says the odd, like when k is odd, it's all one sign, and when k is even, it's all the other sign.
Yeah, but we haven't proved that x is positive. Wait, no, not x. No. Oh. Yeah, because we haven't assumed anything about like. Uh,
R over s.
hmm.
I mean, if
We also don't know that the continued fraction of r over s matches the continued fraction of x. So it's like,
oh no, it does for the first k. Yeah,
does it have to?
that's by definition. That's how we define k plus 1.
What?
These are the same a's. Yeah.
Really? Why are they the same?
Huh?
Why are they the same?
Oh no, because we let we let the alpha k plus 1 be like anything. You know. So as long as
Yeah.
as long as you're allowed to let it be anything, you can let all the first views be the same. Yeah. Because you can just
be anything.
as long as a isn't equal to any of those quotients.
What?
Wait, I thought we went over this. So
What the?
so we have alpha equals like a1 plus 1 on a2, yeah?
Mm.
Plus 1 on alpha k plus 1, yeah?
Yeah.
So we're letting like we're literally saying that as long as we let this thing be kind of um, dependent on all these alpha A1s and alpha, we can actually always write alpha like this for any A1s, integer A1s. Any positive integers A1 up to AK
We're trying to prove that alpha k plus 1 is greater than 1.
greater than or equal to 1. Yeah.
But, like, we don't know that yet, so
Yeah.
it could literally be any.
Oh yeah. So I guess it's kind of like yeah, that's true. So it's kind of an abusive notation then. Yeah.
Because the problem is, like, I don't. Because they say as k is odd, we have it's epsilon is positive. But then that's assuming that the alpha k plus 1 is, like, positive or something of the sort.
Yeah. So if k is odd,
But
yeah. Yeah, actually that's kind of true, right?
Yeah.
I don't know. Maybe we can just
I
because
think it can be fixed by, like, say, depending on if r over s is greater or less than, you make it
yeah,
odd or even. Like, I don't know why they just made it hard.
yeah. So I guess for us, like we can keep in our mind that our thing is always positive. You know what I mean? Because we're always doing the Pell's equation. So
Yeah, or just for our purpose.
so for Pell's equation, it will always be positive. You know?
Okay.
Yeah. So Alex makes a good point because I'm saying like the continued fraction, the odd parts are always greater or less, right?
Yeah.
But that's not actually the continued fraction. You know what I'm saying? We're not actually even assuming it's the continued fraction. You know what I'm saying?
Yeah.
So actually, we might even need like for proper rigor to even kind of prove this, right? But so this held true more generally for like we definitely convinced ourselves when it was true for continued fractions and the tail of the continued fraction. But is it true for like negative tails and stuff like this, right? So I think the thing that when we actually did it, we actually I remember it was saying it was true just for complex numbers. so so it should be all right. Okay. All right. I guess yeah.
Just assume it's greater. Is it greater? Wait, hold on.
But Liam should at least be able to verify that we get up to here, right? He looks like he's looking at it for the first time. It's very worrying.
So when you get assuming that's right, then you just sub in x, and then you get.
Yeah. So
when you sub in x,
so this thing here is
minus
one, right?
k.
It's using this thing. Okay.
One.
Let's
We're
pick
assuming odd. So
k is odd, yeah.
it's -1.
Oh, it's -1, but it's the negative of that. It's like backwards because it's got the pk at the negative.
It's like,
So here's the pk is positive. Here the pk is negative.
So you get k plus 1 equals that thing, and then you sub in the k -1, k -1, but minus. Where did that go?
So here's the pk is positive. Here the pk is negative.
Disappear. Oh no. Wait. I'll just do myself.
Wait, which part are you doing?
I'm just doing the next one. The part where you sub in the epsilon.
Oh, okay. So I guess I'm up to here now.
Yeah, I need to get up there. Okay, so we have x.
Where's Liam up to?
1 equals q k minus 1 x minus q. Q k x with x. put alpha.
Okay, obviously we want to show the numerator is greater than or equal to the denominator for it to be greater than or equal to 1, right?
Yeah.
Alpha. We want to replace the alpha. Alpha equals epsilon plus qk over q. This equals qk minus 1 epsilon plus qk over plus qk minus over is that true? Yeah, okay. Minus qk plus qk minus minus 1. Okay, now you times the top and bottom by qk. You get qk minus 1 qk epsilon plus qk minus 1 qk minus qk plus 1 qk, and then I can sub in that thing. And that's 1. This is. Wait, what? I got plus 1. Oh, wait, no, it's negative because of. Wait, what? Ah! Am I tripping? Oh, maybe they negative first. Okay, I'll keep it. Minus qk squared. Okay, I got the qk squared epsilon. And then that becomes minus qk. Was that cancelled? Minus qk pk. Pk minus 1. What? Hold on. What the?
Yeah, I guess we might have to do this again for Liam's benefit, but
Am I tripping?
let's see if you can remember what happened.
What is going on here? Okay, so Pn minus 1. Qn minus 1 is positive here, so this is minus 1. That equals qk minus 1 q1 minus 1 over. Just need to work out the bottom. What happens at the bottom? What the? How did they just cancel? I swear they'll cancel. Actually. Did I copy it wrong? Oh wait, no, I didn't. Qk minus 1 q. I copied that part. Qk minus. So now this is qk minus 1 qk, and that one's q p pk times qk. That cancels out times qk. Ah. Does this cancel? How does this cancel? I swear this doesn't. What happened? Minus q minus q. Oh, wait, I think I'm retarded. Yeah, okay, I'm just retarded. No.
Have you guys all got this? Do you understand?
I know what happens here. Wait, what happens to the denominator? I'm just bad at algebra.
Wait, there's only one button in the chat. Denominator.
Yeah, I think I'm just bad at algebra.
Which one are you up to? This one?
Yeah, I'm just trying to get the denominator.
This?
Yeah,
Oh, because we times qk on both top and bottom.
yeah. So then you get
Then you get qk pk minus 1
QK.
minus epsilon qk minus 1.
I got the topic.
Yeah, and the bottom is just epsilon qk times qk, which is qk squared.
Epsilon QK times. What? Wait. P. Oh.
I guess.
Oh.
Yeah, I did the negative of the top and the negative of the bottom.
Oh, wait. Oh, yeah, you just can't. Okay, I got that. Wait, how did I not get that before? How did I not get that?
It's kind of a nice little proof, but it's actually like not quite correct, is it? Because of Alex's issues. Like, it's not clear that it's positive, is it?
QKX plus PK, and then I sub it in with QK, and then I get epsilon. That equals minus QK epsilon plus PK minus PK. This cancels, and then I square. Alright, and then I reverse the top because.
Okay, and then you get to here, right?
Yeah. I got
And
it.
to get the top to be greater than the bottom,
Alright.
basically you need to show that this thing is less than 1, right?
Yeah.
Epsilon is by definition less than 1 on 2k squared, or qk squared, right? So,
1
so for
minus Q. They
so for
factored
this-
out the.
for this to be less than 1, you just need qk times qk minus 1 to be less than qk
So
squared.
they get that.
Yeah.
We need the epsilon QK.
And you just need qk minus 1 to be less than qk.
QK
Yeah.
minus 1 equals epsilon times QK
Even
squared
QK minus 1 is less than QK.
Yeah, because qk is equal to something plus equals qk minus 1 plus times something positive plus.
Wait, so this you get epsilon. You want this to be less than 1. So what happens? This is epsilon is basically like less than 1 over 2. And then you just need QK minus 1. And what did you get with the recurrence relation? Why is QK minus 1 less than QK? I forgot. Okay, I just factor this out. E times QK. Bro, what? How did that happen? QK minus 1. Oh, it has to be less, surely. Because you're literally adding another term. But how do you do it with the recurrence?
Alright, so how is everyone? Are we up to the end
Oh
of
yeah,
this?
you add a. Oh yeah, okay, I get it. I think I get it. Yeah, you're literally adding it times something. Like, I see.
Okay.
I understand.
So maybe let's put it into
And then it's
context.
done. Except for the sus part.
Yeah, so I think we can make it not sus in our context. What the? Okay, I'm gonna erase everything now, okay? So, see if you still remember it. So the whole point of this is to show that. So before we showed that the Pell's equations, the continued fractions, every every period basically, or every 2 periods gives you a solution to Pell's equation. You know? Now we want to show that every solution to Pell's equation has to come from a continued fraction. You know? So laggy. So this is essentially this. So you have Pell's equation here. And so if you kind of rewrite this, you get, so this is actually obviously greater than 0 as well. And so you see that Pell's equation here, any solution has to give you an approximation of root n that's within 2y squared, okay? Should be 2y squared. Okay. So I guess this is begin prop. And then I guess It's kind of right after this. Alright, do you guys still remember the proof or the theorem statement? Let's see, let's state the theorem. How we want to state it. Okay, so one question I have is like, so why is this sort of still not the converse? Like, what are we still missing, by the way? Like, is this the actual converse or not?
Out of the rational thing that equals the alpha.
Yeah.
Does alpha have unique? Surely it does. Yeah, probably.
So this may not be the continued fraction. We want to prove that it is. Okay. You guys remember what the first step was?
The first step. What does it say? What is the current? Suffices to show this is really involved. So first you need the alpha k plus. Wait, no. Okay. After you get the alpha k plus 1 thing, need the recurrence. You need recurrence. And then you're like, okay, so recurrence has
Alpha.
oh yeah, and the recurrence, and then you solve for alpha k plus 1 in the recurrence.
Yeah. K plus 1 P K plus PK minus 1. So we should probably check that this actually does work at some point for like complex continued fractions even. Mm. Okay, I think we can actually skip a lot of steps and just write to the final answer. So it's 1, so it's is it alpha minus? Oh, so we have it the other way now, is it? Have it the other way. Alpha. Oh no, we shouldn't skip to the final step. K plus 1. So you had a chance to actually learn this. I don't know why I'm doing this again if you're not going to do it. You wasted 2 chances. Okay, so we're here make alpha k plus 1 the subject, okay? So the bottom is alpha k pk. The bottom is alpha qk minus alpha pk. Wait, what is it? Oh, it's just pk. It's just alpha qk minus pk. And the top should be pk minus 1 minus alpha qk minus 1. Okay, so she get you like this. Okay, for some reason I have a square closed bracket here, but hmm. Yeah, somehow times the top and bottom. So that's negative.
Pretty sure it still works without it.
Yeah.
And that works.
Yeah, I guess this makes more sense to write negative. And then negative. Um, to times it by QK. Hmm. Yeah, you kind of want to say it's within 2QK squared of alpha. Yeah, like you're essentially replacing alpha by PK over QK. So it's that. Minus alpha. Wait, it's already minus alpha. That's plus. And then you go to minus minus pk, qk minus 1. Yeah. Yeah, and then pick the parity of k, so that's... Well, let's do this. Just switch the signs of the top and bottom. Oh wait, I should have still kept that as minus alpha. Sorry. Let's make that a minus. Yeah. So pick parity of k, so that... Um, yeah. So this thing here is greater than or equal to this thing here. Or in other words, um, this thing here times plus Okay, but okay, so that's enough time for you to figure out what was wrong. Is it quite the converse or not?
Is it?
Is this the converse?
Is it the concept? No. Sus.
Okay, so there's one more thing. Like just because it's in the continued fraction, right? Just because it's in the continued fraction doesn't mean that um it doesn't mean it's the part that we specified in the other theorem, right? The other theorem said it was basically every period or 2 periods. Every every even number of periods. Or like every multiple of the periods where it's like even and
Oh, right, the book.
yeah.
Ah.
So this might tell us that it occurs at like an even, yeah, whatever one gave us the +1 sign. But so this is like k is even.
Sus.
Yeah, and in the proof you're meant to kind of choose the parity at the start, but we chose it when we chose it when we needed it.
So how did you deal with the epsilon being positive?
And the epsilon being positive.
Yeah.
How to deal with it?
It's like,
Well, here we just assumed it was positive because we started with
ah,
we didn't have any absolute values.
okay. So it is given.
Yeah,
So that, I mean, that's good for enough for
Pell's.
our purposes.
Indeed.
Okay.
Yeah, so we don't actually know where this equation is. Um, so it might be good. I don't know. Do you want to keep going with this, or do you want to take a break and look at another approach to Pell's equations? Yeah, I guess Justin hasn't actually seen part A, has he?
Part A.
Part A to the question.
How did you guys do part A?
It's N7. Yeah, I guess we can take a little break from this and do that. Yeah, 3 and 4, yeah. Mod 7. Yeah, I guess there's something interesting there. So, I mean,
Recording stopped. Recording in progress.
like, if you look at the, like, if you look at how the Part B works, it's not surprising that, like, Part A is basically saying that it has to be Pell's equation, okay? It's like, there's no other way about it. Okay? And so, um, yeah, I guess this is where, like, 2016 EGMO question 6, knowing that it's a bit of a spoiler, because it kind of made the question now hard enough for that to be a possibility. Whereas normally on prep problems, I don't think N7
I guess
could.
I didn't really think about the where it came from.
Yeah.
I just saw Pell's and I was like, this is probably one way of
So it was actually EGMO 2016
I
Q6. So
didn't
it's actually
think it was
it's meant to be a hard question, you know? Like,
Yes, I didn't think it would be the only option. I was just like, this is probably
yeah.
possible.
So like if you remember our approach, it was like N equals 2 or 3 A times B, right?
Yeah.
And the way we really got that was by considering like the prime factorization of N, you know?
What? That's interesting.
So if you look at N, it's like P1. It gets a little bit crazy, I mean, with notation. P1, R1, all the way up to P, um, you know, P, K, RK, right? And we're basically, what we're trying to do is we're going to try to get N squared plus, and we know that the other thing has to be a divisor of N squared. Okay. So, we're basically doing something like this. So it's N squared plus, okay, and it's P to the, so we're minusing, I don't know if it's like 2 R1 minus S1 all the way up to say like P I 2RI minus SI. Um, and then there's the stuff in the middle that doesn't get changed. And then there's the stuff at the end which gets plussed on, yeah?
Alright. N squared plus some weird crap.
Yeah. So in some sense the P to the, like the, so we're timesing our N essentially by B over A, right? So the B over A,
N
so
times.
the A is kind of like our P1 S1
Are you timesing N squared or N right?
N squared. Wait, we're timesing N by B over A and we're adding it to N squared.
Oh, okay.
Oh, so there shouldn't be a 2's here. There shouldn't be any 2's here. The 2's come later. So this PI SI, that's our A. And the B would be like our P J T J all the way up to P K T J K, right? Yeah. And if you think about it, it's the same condition, right? Like if you're saying this thing divides P1 to the 4R1, right? Yeah. Yeah. So if you're saying this thing divides that, yeah. But this thing has like basically like a big chunk of common factors, right?
S1P. This is extremely confusing.
Yeah. So it has a big chunk of common factors. So it actually has P1, R1 minus S1 is a common factor. Ri minus Si is a common factor. Pi plus 1 all the way up to P J minus 1.
A and B are co-prime, and then
Yeah, so
you have just a bunch of RJ.
yeah, P. So basically all of this is a common factor, right? So call this like, what do you call this? You can call this N times A over B, right? Or N times B over A. This is called N times B over A. And that entire thing is a common factor, okay? So it's N times B over A times 1 plus, and then here is like, it's P1, it's R1 plus S1 all the way up to Pi. Okay. And the stuff in the middle stays the same. And the stuff at the end, it becomes minus T. I just won't write the end over that. So Rj minus Tj. Okay, so by the same principles as before, yeah? It's basically like, it suffices to consider this part, right?
One, but it's factoring up.
And that part's co-prime to all the it's co-prime to everything before J, right? And it's only not co-prime to stuff after J if the Rj equals the Tj, yeah. Yeah, so I think this kind of thing is kind of difficult to do unless you have sort of the A squared B squared thing in mind.
What the hell?
Because basically you have that, like for this to, so you basically get 1 plus this thing, right? And so this thing is literally like, this is literally,
B over A.
this is literally N times A over B, right? Divides, so whatever the P's are left over, yeah?
I am incredibly confused.
Like the product of PLs such that TL equals RL. And
Let me just. Why do this weird thing where they're like n squared plus n times b over a? Yeah.
this is, I guess, 2 RL.
And then
Yeah.
divides p1 for r1. Yeah, that's pretty clear. Yeah. Is it?
Yeah. So the point is this thing here is less than or equal to B squared, right?
Bruh. Right. So P1 for
Wait, this is,
n. So what's n times p over a times 1 plus?
this is, you could think of this as TL even. Remember RL equals TL. What?
1.
Yeah, I guess originally we had
We have that.
N squared plus
So that's
b over a
n times
n
b
divides n
over
to the 4. And then
Yeah.
we turn this into essentially yeah. We turn this into n b over a outside of
Oh wait, like
n a over
reverse.
b plus 1
Oh,
divides n to the 4.
okay. That makes. Oh, yeah.
Yeah, and then we cancelled a bunch of stuff. But the whole point is this thing here is co-prime to like a lot of stuff.
Wait, so n squared plus b over a and
Yeah, so like this stuff is co-prime to
What's up?
everything that appears in here, right? So the only thing it's not co-prime to are the ones where possibly the TJs equal the RJs, because that's when it doesn't appear, right?
so n b so that inner thing, the one inside it. Yeah, it's like 1 plus some really factory thing. Oh. So, oh yeah, so it's like it's not co-prime to like the when stuff disappears. Oh, okay.
I also encourage Liam not to say stuff like dead chat, because that kind of kills the chat, okay? It's the only thing in the chat.
Stop it! He's already dead.
Yeah, you get that? So,
Wait, it's like, wait, I forgot. Wait, n squared plus b over a n. Do we already prove that's like? Oh, are we just assuming that divides n?
yeah, that's the assumption, yeah.
Ah, yeah.
Yeah, and
What about
so
this
basically, like, this thing
Oh,
divides a whole bunch of p's times together, right? And for them to divide a whole bunch of p's times together, it has to be the p's that don't appear in this block, yeah? Because that's co-prime to it's co-prime to that block, yeah? It's co-prime to every p in that block.
so,
Because you added 1, right?
so everything except for like RJ plus TJ.
Yeah.
Alright.
Okay. So that means the RJ has to equal the TJ for it to be in the stuff that's being divided, yeah? But that's less than b squared. You see that?
Oh, nice. So 1 plus. Yeah, okay, so that
So
thing
b squared
divides this
equals the product.
product. PL2 Hmm. So that's the.
This is like
Oh yeah, we're assuming that this still. Wait, like
well, this m. This m equals j
brain
to
is
k.
confusion. It's an NB over. Wait. Yeah, so that obviously has to divide and over. What? Okay, clearly I didn't actually understand something. But how do you get that 1 plus n a over b? Like that thing divides like n squared.
Which thing divides n squared?
But
This thing here.
wait, no, that's not. But yeah, this thing divides.
Oh, okay. So this thing here, right? That's this
Like
thing.
that. Yeah.
Yeah. And so it divides whatever part has this part killed, right? Because that's got all the primes there. So you need the powers to be 0 for it to be.
Oh, so 1 plus this shit. So it's co-prime with that. That doesn't divide. Wait.
Yeah, because if the
Are you saying like it actually divides that or just divides like some factor. Wait. Oh, it has to divide if it divides a factor. I'm dumb. Wait, hold on.
I need to get the logic.
Oh, yeah, okay. Yeah. Yeah, because everything you get co-prime with, you just get rid of it. Yeah. You just got rid of the co-prime stuff
Yeah.
from the n to the 4 to the n squared.
What should do?
Okay. How do you get like n squared?
N squared.
Like, this divides n squared.
What the Alex?
Hmm?
Because B on AN is basically your A, right?
B on A n, that's A.
Yeah, and you got n squared plus A divided.
Oh. Wait, no, that's n A over B, not B over A.
Oh yeah,
That's not the same thing.
true.
You're kind of paying too little attention to be helpful, you know? You're just annoying.
Well, that's not the same.
You should stop not paying attention. That's what you should. It's the order of things.
How did you get its the middle divide? Oh wait, no, I'm stupid. Wait, no, I'm not stupid, man. That was legit. Okay, my number theory is kind of lacking. I don't even know when I'm right.
Uh-huh. Yeah. So what happens is the n cancels. So
Yeah.
here,
You get
this
the
n
n
cancels the
cancels
n
the
cube.
n. What
And
happens
then
with the b over n?
So the b. Remember the b has the p to the r's, right? So here's the p to the 2r. Yeah. So this is like pj to the 2rj. Yeah.
Mm.
Sorry, 3rj, right?
Oh yeah,
This
it's three,
b
right?
b has the p to the rj. Yeah. And so that cancels to make it 2rj. That's why it's a 2. Yeah.
2r. What? Ah, it's only those ones.
Yeah.
Oh. Wait. So b over. Let me check. B has the S. Let me check. Where did all this come from?
Yeah, so I guess if Justin understands that claim, there's basically two claims I'm making. So this thing here,
Yeah, this shit's complicated.
this thing's here is less than b squared, and this thing here is less than a squared. Or bigger than a squared, sorry. So then the previous kind of arguments apply.
Wait. Dude, how does this look? Honestly, so B is B over A. That's like,
So the a and the b are kind of separate, yeah?
oh yeah, A just is just not there.
Yeah. The a's are all gone anyway, yeah?
Like, how do you know B over A? It's not.
Huh?
Oh wait.
Like the b is like the later part of the p's, and the a is the earlier
Yeah, A
part.
is that one, and then B is that one. But then how do you cancel N?
The n is just here. It's just a factor.
Like once you cancel it, don't you like you even get an integer?
Oh no, you get this thing.
Like once you cancel the N, you get like B over. You get N plus B over A, and then B over A is not.
Wait, n over b over a.
What?
Yeah, like you're not really canceling the n separately. You're kind of just canceling all the primes that you know what I'm saying.
Okay, let's just cancel them together.
You're basically canceling two lots of all the primes in B. Yeah.
Alright, let me do that real quick. So you know N times A over B And then over B has to be an integer, right? But assuming the B powers are small enough. Yeah. That makes sense.
Yeah, like you're basically trying to get this from
Well,
four
I just need to
to
figure out
two.
I need to figure out how many. Okay. The B's, they basically introduce a bunch of T. Is it T? Yeah, okay. Hmm. They give you some T's. But how does it cancel all the way down to 2 from 3?
Yeah, because there's the N, there's the ones from N, right? And then there's the one from B. So there's two of those.
Really? Yeah.
Like you can think of these two as like you can think of this as N over A times B, right?
N over A times B. Yeah, okay. So N has the.
So because A has nothing to do with B, the N over A has the same as the B. It's essentially B squared here, right? As far as the primes are concerned.
B squared.
Yeah.
Shit, I'm confused now.
Basically treating this like B squared.
Oh, yeah, because N has like at least the B powers
Yeah.
on the B P's.
Yeah, and only the ones in B can actually remain here, right? Because they're the ones that
Okay,
can be zero.
so that has at least B squared. Wait, how does that cancel the N?
Because here there's like B to the 4 basically here, right?
Oh.
And you cancel 2 of the B squareds here.
Wait, how does that just be the 4? N to the
Oh, because only the primes in B we really care about, right?
Like, it has more.
There has other primes, but they're co-primed to everything here, so we're not gonna get anything.
Yeah, so we only care about the B prime.
Yeah, and then
N?
2 of them cancel with this B squared.
Wait, but then how do you, like.
Huh?
I'm confused.
Yeah, so there's like B to the 4 worth of primes here, right?
Is it? Okay, yeah, there is B to the 4.
Okay, and then B squared cancels with that B to the 4, and then this thing divides the other B squared.
Wait, but so there's at least B to the 4 then. That doesn't mean there's B to the 4.
Oh no, there's exactly B to the 4 then.
Really?
Yeah.
What? That's. How? How is that possible?
Like,
Fractal 4.
because N is just B times like. Okay, well not sorry, not B exactly. It's this stuff. When the T is equal to the RL,
Oh.
that part there's exactly 4 lots because the R is equal to the T. Remember?
If I equals T, then.
So like if R equals T because N to the
Oh,
4.
right, okay, now I get.
Yeah.
Because. Oh, yeah, you're taking that special case.
Yeah, because if R equals T,
Oh, yeah, and that's.
then the powers exactly match. Yeah.
Okay. And then that's less than or equal to B squared because it's just a part of B squared.
It's just a part of B squared. Yeah.
Okay, and then that N A over B
Yeah.
is. Well, A is less than.
Yeah. The N A over B has to be greater than or equal to A squared, right?
N times
Because N has an A in it.
A, and then A has.
An A in it.
And, wait, N over B.
And then B doesn't touch A, right? So
Yeah.
there's at least A squared, right?
Yeah.
Alright, good.
Bro.
Alright, sick. Oh, what the?
Uh,
That's not even the same.
you drew on different.
Alright, so yeah, the conclusion of that is so basically if B squared, because remember like it's N squared plus B over AN, right? That's like the divisor. So for B over A has to be less than 2, right? No, it has to be less than 2n, yeah?
Mm.
So B over A squared has to be less than 4, right? So it's the same argument as before.
Yeah.
Because this is smaller than B squared. So something smaller than B squared, and this is bigger than 1 plus A squared, right? Yeah? Something small.
B squared is.
So B squared is less than or equal to 4A squared, right?
Mm-hmm.
And
Yeah. And then b squared over here.
and so the point is, like, if something divides something even smaller than b squared, the multiple can't be like 4, right? It has to be 2 or 3.
Ah.
So here it's equal. So the multiple has to be 2 or 3, right?
So it's like b squared is less than or equal to 4a squared. But then we're dealing with 1 plus a squared
Yeah.
on this side. Wait,
Yeah.
less than. Wait, we're doing less than that.
Yeah.
Eh?
Yeah, so it's actually crazy because
Wait. So 1 plus n a over b. Wait, that's. Oh, wait, we said that was greater than. Oh, shit, I'm dumb. Oh, yeah, okay. Yeah. So. Oh, yeah, so 1 plus a squared is like greater than a squared, and then 1 plus n a over b is greater than 1 plus.
yeah.
Oh, okay. Then. And that. On that side. Okay.
So like there's actually literally no room, right?
So that has to be 2 or 3, yeah.
It has to be
Wait,
2
I
or
got
3.
something extremely simple.
Yeah.
Yeah, just.
So basically
Bro.
has to not only does it have to be 2 or 3 because it's 2 or 3, like not only like this basically has to equal b squared, right?
Mm.
And this basically has to equal a squared. Like it's essentially like all these primes in the middle here, yeah. They can't exist essentially. They have to be like
Oh, yeah.
because these are all
So-
contributing here, right?
Wait, so. Oh, yeah. So that one contributes to the.
Yeah.
Oh, yeah, that adds stuff.
Because if something there is not, so
And
there's only a few cases, right? Because if there is something there, it has to be 2 or 3, right?
Yeah, it can't be
And if it's
anything.
2 or 3, then all of that just equals b squared, right? Because it can't even multiply that anymore, right?
2 or 3. Then.
So like if that's 2 or 3, then this becomes 1 plus 2a squared or 1 plus 3a squared, right? And then this has to just be b squared, right? Right?
So the b part cancels with the b part of the n.
Yeah.
Oh, yeah, and then you're just left with the a part and the stuff that
Yeah.
has to be 2 or 3.
Yeah. So that's one case done. Then it's Pell's equation, right? 2 or
So-
3. So then the only other case of there's nothing in the middle here, right? There's nothing in the middle there. Okay.
Wait, n plus n a over. Oh, yeah, and then there's like just 2 cases.
Yeah, then there's like one prime in the B part is like like
that has to be literally b squared. Oh, yeah, because it's co-prime with all the a shit. And then it's also co-prime with all the.
yeah.
Wait. Oh, no.
So then you get like B squared on 2 equals like 1 plus A squared, right? Or you get like 1 plus 2A squared equals B squared. Like in all the cases, I think you just get like Pell's equation.
Wait, this is so confusing.
Yeah, it's a little bit confusing.
It's so confusing. Wait, so 1 plus n a. So that's co-prime with.
So there's maybe like 3 cases, but they're all kind of easy to see.
So if it's like 2 or 3. But if that thing is 2. Oh, yeah, because we're literally saying that. Yeah, because the product is. No, it's not.
Yeah, and if it's 2 or 3, then it has to equal B squared, right?
So if it's 2 or 3, that's less than or equal to b squared. But, like, you already said.
Yeah, like it can't be less because then it'd be a divisor, right? And then B squared would be too big again. Oh,
Wait.
okay.
Yeah, I'll just... So 1 plus... I don't
Is
know.
Justin with us following? Is it all pretty good?
I am confused. Deep confusion.
Okay, Justin's following. Okay, that's good.
1 plus n a so the 1 plus 2a squared. 1 plus 2a squared. Or 3a squared. What happens here?
Yeah. Yeah, so you can kind of see that the S's have to basically equal to R's as well. Yeah. So basically all but one S or T is equal to R.
So
And it has to occur on one of the primes labeled 2 or 3. Yeah, it's either one of
1 plus 2a. Um, hmm. That divides. It somehow divides that. Okay. This part of b squared.
yeah.
But. Hmm.
Yeah, so essentially there's only really two cases. Either 3 or 2 as the
I'm
prime.
so confused. What the hell? Wait, how is it like. If it's 2 or.
Okay, I guess it's still more. But like it's either 2 or 3 as the prime, and then
Yeah.
the prime can occur on the S, on the middle part, or the T, right?
Hmm.
And we already did the middle part.
Wait, what happens in the middle part?
Oh,
If it's in the middle.
if it's in the middle part, then it's just straight up like our example, like n equals 2ab from before, kind of thing.
Yeah.
'Cause-
Oh, wait, and then we just. Wait, why does it have to equal then?
oh,
Equal
because
this.
if it's 2 in the middle part, then this will be like at least 1 plus 2a squared, right?
Yeah.
And so then this has to be equal to b squared because it can't get any bigger, right?
1 plus 2a squared. Is that at least b squared? Wait, what?
No, because if this was a factor of b squared, then b squared would be even double this, right? So then it'd be 4a squared. Will be more than 4a squared. And so, you know what I'm saying? Like this is like if this isn't all of b squared, then b squared's even bigger and it's at least double, right?
Wait, so here to. Oh, wait, right. This is all the shit that's in the end. Oh, wait, okay.
Yeah.
Oh, so that's just like a bunch of primes of that.
Yeah.
And then A has like those primes of. Wait. What is going on?
Yeah, so like because the middle part doesn't interact with a or b, right? So if you have a 2 there, it's just purely an extra 2 in there.
Yeah.
Right? And so this thing is like 1 plus 2a squared, right? So this thing here can't be a factor of b squared. Like purely like a proper factor because then b squared will be at least double this thing, which is 2a squared. It's going to be at least 4a squared plus 1, right?
So if this divides 1 plus 2a squared divides that.
Liam.
It's in the mid.
I already have a water bottle.
Is it full?
So that's.
If it's like, I don't think I'll be able to finish another whole water bottle.
Right, don't open it then. Put it there.
But what?
Just leave it. Be quiet.
So 1 plus 2. 1 plus 2a squared. It divides b squared, but then. Because that's a part of b squared. Okay, yeah. But
So
then,
that's the equal b squared. It's already as big as it could be, right?
but then, like, the 2 is literally doing nothing.
Yeah, and then so then the A can't get any bigger either. So all the A's have to be killed. So all the R's are equal to the S's. Right, so this literally has to equal 1 plus 2a squared, and this has to equal b squared. And so it's b squared equals 1 plus 2a squared.
Bro, my brain no what.
Oh,
That's his head.
okay. Well, I guess, so like b squared has to be smaller than 4a squared, right? Yeah.
Yeah.
So b squared, if it's divisible by something bigger than 1 plus 2a squared, it has to equal 1 plus 2a squared, right?
Oh. Right, so b squared is smaller than or equal to is it at
Yeah.
most 4a squared. Then this is 1 plus 2a squared.
Yeah.
But at least 1 plus 2a squared, but we know it.
Yeah. And so not only, so b squared has to equal that, right? So which means b squared equals this as well, right?
Okay.
And then this actually has to also equal
yeah.
2a squared, because if it was any smaller, it'd be like at least 4a squared, right?
Right, so this has to equal. Like, we know it's at least 2.
Yeah, but it has to equal 2a squared because it's a factor of this, right? So if it's any bigger, it has to be at least 4a squared. Does that make sense?
2RL. N. Alright, well. So we know N is that. Okay, we've set that middle part to 2. And then that side has stuff. Oh yeah, the B's don't interact with the A, so we're saying.
Yeah. Does that make sense?
And the S's don't. Oh wait, are we claiming the T's equal to
Yeah. If the b squared equal, if this is equal, right? Then all the t's equal to all the r's. Yeah. But like.
Oh yeah, because if any of them don't equal, then there's at least 2.
Yeah, exactly. Not it's not gonna be too big, right?
Okay.
So
oh yeah, that makes
so there could be at most one that's not equal, and that's a 2 or a 3. Yeah. But if that happens, then all
we
the
have
others.
we have the 1 plus.
Yeah, I mean this. So there might not be a 2 here, but if there is a 2 there. Yeah. So I guess are you happy with the case if there's a 2 or 3 coming from the middle part?
So if there's 2 or 3 coming from the middle, then
Then that happens. You get a 2 here or a 3, right?
2
And
or
that'll
3
force
from
b
the
squared equal.
end.
So all the t's are equal to all the r's, and then the b squared equals that, and then there's nothing. The n over b is exactly just a. 2 times a squared, and then you get the Pell's equation, and you're done.
So you can't have anything. Yeah, okay. So the T's have to equal the R's, so we'll always
Yeah.
get 4A,
Yeah, exactly.
and then. Oh yeah, and then it's just 2A.
Yeah. So the middle part's done, right? So then literally now this is just.
So yeah.
There's no middle part. It's literally just a and b now. Yeah. So n doesn't have a middle part. So n times a over b is literally kind of more just like. It's kind of like just a squared, really. But it could be a 2 or a 3 that could come from the b or the a, right?
So N is that. We're assuming the A's. N over B. That doesn't get rid of any. Then the A becomes. Okay, and then we just have a 2 over 2 or 3. If it's 4, then it's more than 4. Okay, so
Yeah. So
it has to come from the A or the.
Yeah.
Okay.
So it could be a 1 plus 2a squared again, or 1 plus 3a squared coming from the a part. But then again, it has to equal b squared, right? And then,
It has to equal. Because like
yeah,
because it's still coming from something.
yeah.
So
And there's sort of, yeah, you might even be able to prove that it can't be in the other parts. But if it was part of the b,
it's the one.
what does Justin think? Does this make sense?
Like 2 times that, then that would be illegal. Alright. Then that's the same logic. So then, okay, that still equals b squared.
Yeah.
Okay, now what do we do? So now, we know that the other. Okay, so if it's on the left, if the 2 or the 3 comes from the a part, then still forces the r's to equal to t's.
Mm.
Yeah, because like,
Yeah, like
because if you multiply like 2 or 3 at all, it's still.
yeah,
Yeah,
like
so that
essentially
still works.
all the r's equal like t's, and all the s
Oh
equals
yeah, and the
r's except
middle
for
part
1.
shouldn't exist.
Yeah, in the other case we don't have a middle part. Yeah.
Okay. Like, so if the 2 or the 3 comes from the a's, it's still works.
If it comes from the s bits, then um yeah.
What about the other part?
If 2 over 3 comes from the a, then you get 1 plus 2a squared, and then that has to equal b squared, right? If the 2 over 3 come from the b,
What
then
happens
this
if it
thing
comes
is,
from b?
so this thing becomes like a third of or a half of b squared on the right, yeah?
Wait, a third or a half?
Because this will no longer be equal to b squared, yeah? Because it'll be off by 2 or 3, yeah?
Wait, so this TL equals. Wait, how's it not equal? Oh wait, no. That's a fact. Yeah. Okay.
But then if that's the case, then the other thing has to equal a squared, right? And so the n over
T.
b equals a.
Oh wait, because there's only one factor of 2 and 3. Oh, yeah, okay. Wait, 2 or 3. So then it can't be. Yeah, it can't be equal to b squared.
I think that's just a contradiction, right? If it's in the b part.
What happens? So this is a b part.
Because if it's
That.
in the b part, it has to equal 1 plus a squared, right?
Wait, is it?
Because it's 1 plus a squared equals a third of b squared, right? So it's not even b squared. So like 1 plus a squared equals a half of b squared is too big, right?
1 plus.
1 plus like 2a squared equals half b squared is too big. Because then b squared equals
Wait, because
4.
it can't. Oh yeah, because like there's only one factor of 2 and 2 or 3.
Yeah,
So then it can't equal b squared. So then it's like half of it. At least, like at most half.
you know.
Then 1 plus 2a squared. Wait. 1 plus 2a squared equals half of. Yeah, but a is supposed to be. Okay, that's just not. That just doesn't work. Okay.
Yeah.
Hmm.
And so then it has to equal a squared. But if it equals a squared, that means n on b has to equal a, right? N on B has to equal A, but N on B, like, there's a part of, I think N on B is actually equal to 2A, isn't it?
Yeah.
Yeah? That's just a contradiction then.
Well, yeah, that doesn't. Wait, what? What do we assume? 1 plus N A. We can't have any of that.
Yeah.
We don't have the extra 2 or 3. So it's just equal.
You see, then he's actually, he wants to consider all the cases, you see. That's the rigor. Yeah. I guess which case are you up to now? I think I can kind of summarize this.
So we did like the 3 cases.
Yeah, so if the 2 or 3 comes from this part, right? Then
That's like Pell.
then there's gonna be a 2A squared coming from the N, basically.
Yeah.
And then B has to basically all equal, so that's equal to B, that's Pell's, yeah? If it's in the middle, it's the same thing, yeah? That's gonna come out of the N, A squared. But if it's in the B, that's a problem because the B cancels, is gonna have a 2A squared. But then this is gonna also not be the full B, and it's gonna go over 4A squared, right? So it seems like if it's in the A or the middle, it's Pell's, and if it's in the B, it's a contradiction.
And if we have nothing, so like,
Oh yeah, and
if
then if it just equals, it's a
then
contradiction.
There's no 2 or 3, it's just like,
It's just equal, yeah.
then
Oh wait, yeah, if it's just
you just get this, and then you cancel that. You get N equals A, B, and that's not true.
N equals B equals A squared. This doesn't work. Yeah. Alright, we're good.
So what do we do?
So it just proves that it has to be Pell's. Like the A and the B have to be Pell's equation.
The A and the B have to be Pell. Does it have to be A and the B? That's the part I didn't get it.
So what do we prove? So yeah, so we basically proved that N has to equal 2AB. Yeah, or 3AB. I think that's what we proved, right? Sorry, like the N's, so yeah, the N has to equal 2AB or 3AB.
So we just took like the part we okay, so here's the logic. We took the part we add. And then the part we add has like increased indices and then decreased indices.
Yeah.
Okay, and then we let those be A and B. And we do stuff. Okay, so alright, and then when we do that we get like N squared plus N times B over A divides into the 4. Bro, I forgot half the shit.
Don't worry, I think your way is probably still the simplest. This is somewhat of a bash in terms of number theory.
Cause like you just take the prime factor.
Yeah, this is somewhat of a bash. So
Yeah, I was thinking about going this route, but like I'm.
But this basically proves that like the examples that we found were the only examples. You know, It has to be n equals 2ab or 10 n equals 3.
Yeah.
Okay. Okay, and it's very directly Pells, yeah. Yours is kind of like a little bit harder to see its Pells, but you're basically done still, right? So I think your thing is pretty much exactly the same as Evan Chen's thing.
Evan Chen, really?
So your
What?
n squared plus.
I went to Evan Chen route.
So you did n squared plus a, right?
Yeah.
So
Divides n to the 4. And I did
Then-
difference of squares on the n to the 4.
and then you conclude it divides a squared, right?
Yeah. And then
And because
yeah.
a is less than 2n, right?
Yeah, I did like 4n squared, and then so that has to be like 3 or 2.
Yeah.
It can't
So
be
then
1
a
because
squared has to
a
equal
squared minus a is not squared. So
plus a
it has to be like
2n squared plus a or 3
Yeah.
n squared plus a.
yeah. And
right?
I said like it can't be n squared plus a because then that means a squared minus a equals n squared. That's pretty
It
false.
can't be that, right?
Yeah, that's wrong.
And then I think
then
it's
I
kind
just checked these two, and
I think it's kind of nice to know how to show these appels, right?
I tried to show their pals, but I haven't exactly.
So this one,
That one is a squared equals 2n squared plus 2a. I did minus 2a.
equals what?
Oh yeah, and
Was it missing a number?
0.
Equals 0. Oh, that's right. You plus 1 on both sides, right?
Yeah, okay, and then I plus 1 on both sides to complete the square.
Yeah, and then you get
And I get
A
like
minus-
a minus 1 squared minus 2n squared equals 1.
so that's appels for
Okay,
a
and then I
minus
did
1.
pels. And it somehow worked, I think. I think I managed to get, like, okay, given that I have a solution for
Yeah,
plus minus 2, then I can get the other plus minus 2.
yeah.
By
Also, I should note that
square.
Alex was able to very quickly show that
I think that's what
part A because you could just consider them
Yeah, I basically
all the
just
possible
did the
mod
mods. I just did
7a
the-
values, right?
Yeah.
So here you can already show part A. So
But
it's
then, like, the hard part is doing the 3n squared plus a part. That's like that's pretty tough thing. But let me see what I do.
okay. So
That part's like the incomplete part of life.
okay, so the exercise we have now, Justin, is turn this into Pell's. So a squared equals 3n squared plus 3a, yeah? Does Liam even remember how to do this? Turn it into Pell's.
I did something really weird. I don't know. There was.
Don't speak, get a piece of paper and do it.
Yeah, let me see. What did I write it?
When you speak, you can say you either know it or
I
you don't
wrote
know
it.
it.
So I did. I moved it. Obviously.
Can you turn this into Pell's equation, Justin? So
Okay,
that's
and
the
then I
exercise.
complete the square. What the fuck? So that's weird. Some weird variation of completing.
Did you get something?
But I need to check how this works because I'm not sure. That seems right. 2 times 3 times 2 is 12. Okay. That's 9. Nice. I did something. Okay, I think I did something that allows you to get solutions with Pell, but I'm not sure how it works with the mods.
Hmm.
Yeah.
Oh wait, so you got the Pell's equation?
I don't know. Wait, let me see. I think I got something that you can solve using Pell. I think, yeah. I don't know. This automatically is. Yeah. So that's even. Yeah. So that means two. Yeah. Okay. So if you get a solution at 4, then it should be. Yeah. Okay. Yeah, and then I was thinking, dude, my brain was so dead back then. So now, yeah, and then because Pell's equation, I can make really large solutions, so I don't have to worry about the going negative part. Then after that comes the part that may or may not work.
So how do we convert this to Pell's equation, Liam?
I forgot.
You actually forgot.
No.
Well, it's a good time to refresh, isn't it?
I have no idea.
Is this what Evan gendered?
Huh?
Is this what Evan gendered?
Oh, he didn't really say all of the steps.
Oh crap! So he did the solution. He wrote his solution.
Yeah.
It's like the solutions in the inequalities.
Mm.
He just wrote.
I felt like our solution was kind of nice. It was very adventurous. We went part B back to part A.
Yeah.
That solution was like kind of.
Evan's Chan's solution was like, it's easy for me and I'm not bothered to write an entire solution. So here's the.
I solved it,
outline
but
of it.
my solution is too long to write on the.
It did not fit into the march.
He was like, problem not worthy of full length solution was basically what he wrote.
Nah, that's cap, yo.
That's literally it.
That's cap.
Wait, I think what you're trying to do, right, is you're trying to complete the square, right?
Yeah.
Mm-hmm.
But it's hard to complete the square when your stuff is like odd and not squares, right?
Yeah.
So like if you want to make it even, you times it by 2, but then 2a squared is not a square, right?
Yeah.
So like
Times it by 4.
you times it by 4, yeah.
He's smart. He's smart. He got it.
You just got to remember what the
It's
idea
500
was.
IQ moves. 500 IQ moves.
Is that what Alex did?
I think that's right.
Equals 0, yeah. And so to complete the square now, it's 2a minus 6. Wait, what? 2a minus 3, right?
2a minus 3.
So you
minus-
just
Wait,
add.
no, you didn't multiply the 3n squared.
Oh, oops. Yeah, so 2a minus 3. Yeah. Squared.
Where minus 12n
12n squared
squared
equals what?
9.
9.
Okay, so it's 9, which is not Pell's.
Okay,
But I thought, what if I just did Pell's and then times 3 to both of them?
oh yeah, it's a square number, right?
Yeah.
Yeah, so you just do Pell and you times by 3.
Okay, now we just need to make sure that if we do that, then a is an integer. Still.
Yeah, I think
But
you
we
can
have
also
2a
you can
minus-
actually also show that like n and a are
But
both
the thing is,
divisible by
a
3.
has to be an integer because 12n squared is even, so
Yeah,
2a minus 3 squared has to be odd.
Yeah.
So 2a minus 3 is odd, and then a is. And then
yeah.
a
I
is
think
an
there's
integer,
lots of
so
things. Yeah,
it
you do,
works.
m is n divided by 3 also works.
Yeah,
It's
yeah.
like minus, and then a is also divisible by 3. So equal to b,
A is
and that's
divisible.
equal to 1. Yeah. So both a and n are divisible by 3.
Oh yeah.
Yeah.
Wait, a is.
Because
Oh yeah, a is obviously divisible.
a is divisible by 3, right?
Yeah. And then n is.
And then
N
n
is. Oh wait, yeah, because
n is
3n squared is divisible by 9.
9,
now.
yeah.
So now n is divisible by 3. Okay, so then you do n
Yeah.
over 3. Okay, and then divisible.
But it's the same as what you're
Okay.
saying, because finding the solution times by 9 is saying that,
Yeah, okay.
so they're equivalent.
That works. Alright, so now it's Pell's and now rule. Okay, now we need to deal with mod.
Yeah, so I think, Alex, without you knowing what the actual solutions are, you were able to deduce that they had to be like 1 and 6 here, and the other one had to be 2 and 5, or 0, right?
I think it's just like. Yeah.
But if you actually knew the solutions,
I
you
think they can both be 0. I don't know. I forgot.
yeah, like, I think for one of the equations, it could be like 0, 2, or minus 2, yeah? For the solutions.
Let me check.
Solutions for n, yeah?
I think for the 2, it could be like. 2 can be all of them actually.
Oh, really? Oh, so they're different Pell's equations are the ones
But
we
then
see.
like the 3 can only be like 0 or 1 minus 1. I don't know. So, something like that. But the concept is if you manage to find one solution, you might be able to like
Yeah.
you might be able to yeet to another solution using the what is it called? The norm thing.
Yeah. Okay, so here is another approach. So let's do another approach. instead of continued fractions. So let's do this.
Recording stopped.
So
Recording in progress.
yeah, so this is the kind of approach like we managed to avoid, which is kind of good, but you should probably still know it. Like basically, I think Alex knows this already. So if you have like a minimal solution, right? Like a naught plus
Minimal solution.
root n b naught, right? It's like minimal, yeah. So maybe like it's just literally the
The
minimal,
smallest A naught plus
the smallest number, yeah, that smallest absolute value, yeah.
smallest real number.
Okay. Then all the solutions of Pell's equations are gotten by the powers of this.
Really? What the? Wait, I
Yeah.
didn't know that.
Oh, you didn't know that?
I thought it could only get some of them.
Get all of them. So what is the test for something to be a Pell equation solution? Is that its conjugate. If you times it by its conjugate, it's 1,
That's
right?
why I wasn't sure that this would work, but then like I was gonna try it and really it would work if
Okay.
I picked the right solution to start with.
Yeah, so I guess we might not have enough time to prove it right now, but I think there's a nice exercise we should do before we leave. So
This is probably the
let's
solution I'm gonna
prove.
submit.
So if you do root 2, right? Then the smallest solution is like 3 over 2, right? So 3 squared minus 2 times 2 squared equals 1, right? So
Yeah.
so the minimum solution is 3 plus 2 root 2, yeah? Okay. And if you take the powers L, right? You should get all the solutions, remember? Alright. What does it mean to take the powers? It means like, for example, if you square it, yeah?
I basically just kept squaring it.
It's like 17 plus like 6, 12, 12 root 2, right? And the other solution, remember, was 17 over 12. Yeah? Okay, so let's prove. So the continued fractions gave us 17 over 12.
It's probably the approach I would have gone with because I only knew how to do this properly.
Yeah.
But I didn't know it was all. So
Yeah,
it
gets you all of them. So it's actually not too hard to prove
but
this.
now I have the knowledge.
It's not too hard to prove this. It's just we don't really have time right now. We should probably do it next time though.
I have the knowledge. Yo.
So 3 over 2, 17 over 12. Like, what do you get from the continued fractions? It's like the previous two. You know what I mean? Sum of the previous. What is it? So it's
So you just use the continued fraction. That's all.
yeah. Let's just do it directly for this case. Like, we know the continued fraction gets all of it now. Yeah. So we actually know that. That's the thing we know. Which is actually it was the other way around when I prepared this. It was the continued fractions. I was going to prove this, but we actually had time to prove the other one. Yeah, so either way, it's basically like what's the continued fraction, right? Like you take 1, 3, and then you do like 2 times 3 plus 1, 2 times 7 plus 1, 2 times 17 plus 7. So it's like 41, right? 2 times 41, 82 plus 17. So 99. What? Is it 99?
2 times
99 and 98. So 239.
So
you just keep going, right?
2 times 41.
2 and then 2 is 12. 2 times 12 plus 5 is 27, 29. 58 is, what the 70?
70, wait.
What a random 140, 160. Yeah, like if you keep going like this, so we're assuming we know that these are the solutions, right? Yeah. And then what I want you guys to do for homework, I guess it's leading up to homework at this point, but I also want to show that 3 plus 2 root 2 to the L as L equals 1, 2 gives you all the solutions as well, yeah? So it's obvious these actually give you solutions, right? It's because if you take something that's conjugate with 1, you take the power, like power respects conjugates, right? It's like not modular arithmetic,
This
but
is
like
the part I actually remember.
circular arithmetic.
It's like complex numbers except I isn't.
Yeah.
I square is like something
Yeah.
else.
Liam should know this from Wiseman, but anyway.
This is like Gala leading.
Okay, so how do we prove this? So maybe like one way to do it is to find out like a sequence definition for this, and compare it to a sequence for this.
Oh, smart. So sequence definition for this.
Yeah, so there's actually a lot of like Pells and continued fractions questions in disguise because they just give you sequences, and then you realize, oh, they're actually the sequences of these.
Hmm. Three. How do you get from one to the other in the continued fraction? So I know I can get from one to the other in the in the powers, obviously. What happens here? That one? It's like a squared plus b squared. No. I am being stupid.
So this one is like pk plus 2 equals 2 p.
3 times. Okay, so you get a plus b is on. Okay, so then you get like a times. You get 3a plus 2. 3a plus 4b. Yeah, and then for the b you get 3b plus 2a. It's like a linearly much because all you can make is just all like
Wait, maybe it's easier to do like 1 plus root 2l. Is that easier to do?
what 1 plus root 2. Wait, that was the thing.
Because then you can get the odd one. You don't have to do. You can get one sequence to get the whole sequence, and then just get the odd parts are equal or the even parts are equal.
Oh yeah, right. Because like when you power minus 1, you get.
Yeah, because 1 plus root 2 is probably one of the square roots of 3 plus 2 root 2, isn't it?
Yeah.
Because 1 plus root 2 squared.
That's what. Well, at least if it would be to be true, yeah.
That is equal to that, right?
Yeah, yeah. Yeah, it works. Alright, let me get this recurrent relation back. So then we go like. Gonna write in the computer science notation. A
Yeah.
equals a plus 1.
Yeah, then we can just directly compare, yeah.
Computer science notation, very stoned. A plus 2b, and then b equals. B equals. Forgot. Crap. It's just b plus. A plus. What? Oh yeah, it's just a plus b. And then what do you get in the continued fraction? You get something weird.
So if you do a plus b root 2 times 1 plus root 2, yeah. Yeah, the continued fraction is just this. That's the definition. It's like super simple. It starts with 1 and 3.
This one depends on 2 previous things, and the power only depends on 1 previous thing, so I'm not confused.
Oh, really?
What?
It only depends on 1 previous thing.
Yeah, because you can just times it. You just times the previous thing by 1 plus root 2.
Oh.
Now I need to convert the 2 previous things to 1 previous thing or vice versa.
Oh, okay. So what is the sequence here then? It's like a plus
well, it's
2b.
not true. Why is it true? I don't know. What the hell?
Oh, so it's like a mixture of p's and q's now.
Yeah. Just like they get
Like this.
They get matrix multiplied.
Yeah. So here you have like pk plus 1 equals like pk plus 2 qk. And qk plus 1 equals pk plus qk.
How
like
do I
this.
do this? Oh, it's.
Oh,
I just verify it manually using induction.
yeah,
Sure.
so you want to show pk plus 1 on qk plus 1.
Surely that
equals.
works. Wait, no, that should just work straight up.
Yeah.
Wait, that should just work straight up. Hold
By
on.
induction.
Let me check. Wait, no, wait. Wait, what was the thing then? Oh yeah. So we want two of these. Want two of these plus one of these. Okay. Wait, yeah. Is it? Wait, is it like two times the last one plus one times the one before it?
For the continued fraction?
Yeah.
So yeah, it's 2 times the previous one plus the one before, yeah.
Okay.
QK
So two
plus
times this one plus the one before. So that's 3a plus 2 4b, and this becomes 2a plus 3b. Then we verify that it is the same. If I add these two, it's 2a plus 3b. If I add this one plus 2 times this one, it's 3a plus 4b. 4b. Yeah, okay, it works.
Wait, what did you do?
I just assumed that the sequences were equal up to a certain point,
Okay.
and then
So
I
like
did,
assume like P1, P2
yeah,
up to PK
yeah.
and Q1, Q2
Well, there's
up to
has to be at
QK.
least two in the sequence,
Yeah.
and so I defined them using the indices.
Oh, okay. So then you do
So
PK plus 1.
so I guess if you have everything up to PK, I write PK and QK in terms of I don't know. I write PK and QK in terms of PK minus 1 and QK.
Oh, okay.
Using the power 1. Using the power definitely.
Oh, okay. You're writing these in terms of the previous ones?
So the one's 4.
Yep. Okay. So
And
then
then I get PK plus 1, QK plus 1.
this is PK minus 1 plus 2 QK minus 1. This is PK minus 1 plus PK minus 1. Yeah. And then you get PK plus 1.
And I get PK plus 1 in both methods, I guess. Using both methods. So now they're all in terms of the K minus 1, so you can easily verify them. So
Oh.
it's just like,
Oh, okay. So then,
just use both methods to calculate.
so one method is it should equal so this is kind of like the P prime K plus 1.
So
It's
you
like
use the continued fractions.
it's like PK plus 2 QK, right? And that's equal to PK minus 1
Okay, so then
plus
you get
2 QK minus 1 plus 2
2
PK minus 1
minus
plus
this
2
2
QK minus 1. And if you do the continued fractions way, you get PK plus, so 2 PK plus PK minus 1, right? Which equals, so the PK minus 1, so the 2 PK is 2 PK minus 1 plus 4 QK minus 1. Alright, so this PK matches this PK, and then this, and then that's 4, yeah?
Yeah.
Oh, very good. And they're equal.
And then this the QK plus 1 is very exclusive.
Yeah, so QK plus 1 is PK plus QK, which is, I'm just going to add this up here. 2 PK minus 1 plus 3 QK minus 1. And here it's 2 QK plus QK minus 1 equals 2 PK minus 1 plus 2 QK minus 1 plus QK minus 1, which is 3K. Ah, very good. Alright. So, if people want to do some homework, I think I'm gonna make Liam use labor hours to do some of this. So things we want to do still, okay. I mean, we probably do some of this in class as well, but we still want to do We want to do this for root 3. Yeah? Okay. So we want to do pretty much the same thing for root 3. We want to also show, like if it's a solution to Pell's equation, like we know if it's a solution to Pell's equation, it's in the continued fraction, right? But we actually also want to show it's like actually in the spot that we said it was last time, okay? Like a direct converse. Yeah?
Yeah.
What?
Like it's not just anywhere in the continued fraction, it's where the like it's basically where the period happens. Yeah?
Oh, the period.
Yeah, so basically the theorem that we did last time was like
Oh, yeah, right.
if you have the square root n, right? And this continued fraction has like period L before it reaches the 2a1, right? And if L is odd, yeah, then the solutions to Pell equations happen to 2L and multiples of 2L.
If it's even, it's just the even.
If it's even, then it happens at multiples of L, yeah? So
Wait, so if it's even, do you not get the minus 1?
yeah, you don't get the minus 1, yeah. Yeah, that's a very good question actually. So you can actually show, for example, so it's actually true, apparently, that like if you do Pell's equation for 3, like x squared minus 3y squared equals minus 1 instead of 1, right? That actually just has no solutions. Okay. It's got no solutions.
Well,
Yeah, and if you remember,
actually, like, continued fraction literally gives everything.
yeah, like if we solved the for 3 last time, and we saw that it always gives you 1 or minus, or I think it gave you 1 or like 2. I think. Like it gave you 1 or minus 2, I think, or something like that. It just didn't give minus 1. Okay. Alright, you guys have any questions?
How does it give me minus 2?
Recording stopped.
There's either... Yeah, just... We need to do it for root 3. Oh.
Damn, this is some advanced number. Very advanced.
So are you able to join us earlier tomorrow, Justin? Okay, maybe 12. Awesome. Okay, so we moved our break up today. We'll move our break back again. So it should be good. Yeah, so there's plenty of stuff to do. I'm gonna post the problem hopefully maybe for tomorrow morning. Alright, see you. End stream. End stream. Oh. No one said hi to Rip. What the?
Oh.
It
Why
went...
does it not show the timestamp?
Yeah, I feel like the streams
It's,
have a little bit of
why am I not surprised that that kid was the one person, aside from us, not in the class to talk in the video?